Hey, everybody, welcome back. We would like to welcome Yuning Chen from Biomimicry Innovation Lab that will be talking materials to us today. Then, depending how long this goes, we'll have probably a little break because we're going to set up a panel discussion, which she's going to be moderating to dig deep into the topic. So welcome, Yuning Chen from Biomimicry Innovation Lab.
Hi, everyone. I'm Yuning. Unfortunately, my colleague can't join today. I'm here at Imperial College Library. I just finished my business trip. So today we're going to sharing about nature-inspired material applied in transportation industry. First of all, a little bit of introduction of ourselves. So Biomimicry Innovation Lab, we are a design consultancy that focuses on sustainable transformation in various industries, focusing on manufacturing, transportation, and agriculture. We mainly do design consultation and also design features in terms of nature-inspired innovation, and also do R&D development with early stage spin-out from the universities. We also, one part of our work, it's also about market research in the field of biomimicry, especially in the UK. We do a biannual research in looking at the whole entire ecosystem in terms of nature-inspired innovation. So you can find the report for our first edition online. To finish this survey, we talked with over 100 and 500 academias in the UK, and also many industry partners. We are seeing a great increase in the biomimicry research and also patents in the field. So our key principle in biomimicry innovation, first of all, is to respect the biological mechanisms. So we've seen a lot of biomimetic studies and research claiming to replicate or emulate biological functions from various organisms, but actually omitting the context that enables the functionalities to actually perform. And then we also focus a lot on complexities, which there's a lot of processes has been advocated by various organizations looking at, surface or shape of biological organisms to create a certain type of innovation. But in nature, actually, all the structures and functions and surfaces are actually part of complex systems. So if we are looking at replicating particular functions, we need to look at how all the trade-offs and interdependencies between each part of within the hierarchy, and also full life cycle mindset in biomimicry innovation, because reducing environmental impact in one point of the chain does not necessarily imply the entire sustainability of the full circle. So these are our main key values. So going back to our topic in automotive, we've seen many environmental challenges happening in the field, especially in terms of an energy crisis, as well as resource shortage, over dependency on precious metals, especially when we are having a great increase in e-vehicles, whereas lacking a lot of raw materials for batteries manufacturing, and also high production footprint and maintenance costs. So how nature-inspired materials can actually help to solve this problem? We proposed three structures into three types of materials into helping to solve the problem. The first one is structural biomimicry materials, whereas the primarily function of this materials is to support or mediate a force, and its key evaluation point would be tensile strength, as well as fracture strength, etc. Whereas functional biomimicry materials aims to replicate a certain function of the biological organisms, such as self-repairing, self-healing, or water repellents. And the third type of nutrients biomaterial will be actually biointegrated materials that incorporated directly biological processes or biomaterials, biological organisms within the material production process. For example, mycelium materials, algae-based polymers, or biomineralization. So all these type of new biomimetic materials can potentially project a future in the automotive industry. And then here we propose 3 visions. The first one is low carbon futures and augmented futures, as well as intelligent futures. And I'll later on explain further about how these material palette can contribute to all these 3 visions. So how do we go about achieving low carbon futures using biomimetic materials? It can go through like fuel efficiency with low drag reduction materials, as well as regenerative biomaterials using, as I mentioned, mycelium or algae-based materials that can actually reduce environmental impact through production, as well as end of life, and energy storage materials such as virus-based battery. So in this vision, I created a material palette that could elaborate a bit further about the future potentials. So shark skin ribless surface, I'm sure everyone's very familiar with how it can reduce drag, and also lightweight structures such as diatoms, how it can actually float in the seawater, whereas made of the material, which is silica, that is denser than the water itself. And also nature fiber reinforcement composite, mycelium, and also a recent development of artificial photosynthesis or water splitting processes for hydrogen energy, and also biobattery development that's based on synthetic biology. So a couple of more detailed case studies. So this one is shark skin surface. I know that shark skin has been developed or discovered more than 40 years, but its actual deployment haven't been really applied in many areas, especially in aircraft industry. And recently, Lufthansa has launched this new shark skin project, collaborated with a chemical company in the UK to develop this shark skin surface on the aircraft, and it will be launched in the Swiss airline for it's projected to reduce thousands of fuel and carbon emission. Well, the second one is mycelium materials, which is getting more and more heat these days, and then many applications can be seen in manufacturing in terms of packaging, building facade, insulation panels, but also there is a very peculiar application in the automotive industry, which is the satellite industry. So researchers have been exploring how mycelium filaments can actually be used to build satellite to avoid problems such as collision risk and end-of-life disposal in the space. And then the third one would be a further case about the virus battery. So this is developed by a team from MIT, where they created a genetically modified virus to form the electrode of a battery, which is expected to reduce the environmental cost of battery electrode manufacturing. And then this project is aimed to create more, to provide greener solutions for electric vehicle charging in the future. And it's actually having a higher charging rate than normal electric batteries, lithium-ion based batteries. So the second one future scenario is augmented futures. It's mainly looking at impact-resistant material, wear-resistant material, and self-healing material. While in nature, nature create material with both strength and toughness. We all know that in synthetic or artificial material development, strength and toughness are more of like a trade-off properties, whereas we wanted to increase the strength of a material, it might decrease the toughness of it itself. But in nature, it kind of achieves both through hierarchical structures. That it activates a strength or roughness at different levels from nano to a macro level. So let's look at some detailed examples. Potentially, we can learn from Holz and Horn about how we can create damage-tolerant composite or impact-resistant surfaces, or we can actually, if we look at our teeth, it is a great example of tough and resilient material in itself. And also our skin surfaces, or if you look at plant or animal skins, they're really great at in self-healing properties. And researchers has been looking at how to create self-healing or replicate self-healing properties in materials through dynamic polymer network or vascular network. And one example would be there are a group of researchers that are actually realize self-healing properties in fiber-reinforced composites, which is widely used, applied to material, especially in the automotive industry. So it's mainly kind of realizing this self-healing properties through replicating the vascular network within human skin and then into a material, the composite material. And then the second example would be spider silk. So spider silk, it's actually a very strong material from nature, whereas it's really hard to actually replicate. So there's a company called Spintex in the UK that they figure out a way to spin spider silk in room temperature to achieve the same level of tensile strength, which is a very cutting edge innovation that we discovered during our survey last year. So the third vision will be intelligent futures. So it includes environmental responsive materials, adaptive materials, and material agency. This session is mainly looking at how natural materials are integrating multifunctionalities inside a single organisms. For example, like plant, they can sense, actuate, and process information at the same time. Or like muscle, it's actually very strong, typical examples of molecular machines that actuate in a very coherent way. So here are the material templates for, sorry, wrong title, from the intelligent futures. We can see how artificial muscles, we can learn from muscles in the way they have multiple degrees of freedom, and how do we achieve the same level of dexterity through way less joint and structural design. And there's a lot of research going on in smart materials, sensing textiles that are heat reactive, and also chemical reactive. And we can see a lot of examples in 4D bioprinting as well, which printing materials. The fourth dimension, of course, is about time. It's about printing materials that can be active and reactive across time in response to environmental stimuli. And then there's also research looking into adaptive nanocomposites that is inspired by sea cucumber, that they can have a reversible stiffness And we can imagine this can be applied in various scenario where materials are required to have multiple properties in response to different environments. And then there's also materials that incorporate living organisms, incorporating their responsiveness and adaptability or resilience to environmental change. The first one is a very famous case. It's bacteria materials developed by MIT Media Lab, that they, through integrating a type of bacteria in the textile, it can react, deform based on the wearer's skin sweating condition. And then the next example is living solar panels. It's actually voltaic material made of microalgae, and then they're currently making them into 3D printed textiles that can power its microelectronics. So we can think about these more textile-based materials applied in the interior design, of a vehicle, especially in the future where EV has a greater space for user experience and interaction design. So some detailed examples might include artificial muscles that researchers looking into how the actuation mechanisms of muscles can enable more diverse locomotion possibilities of robotics, especially like soft robotics for underwater exploration as well. And then the next example would be 3D bioprinting in space. So a lot of new technologies have been looking into how we can actually achieve the same level of manufacturing dexterity or speed in the space, while 3D printing, bioprinting is a great way to looking at it. So there's this example, it's about astronauts bringing this 3D printings gadgets with them to create healing wound bandage in the space. So basically, the advantages of 3D printing in space is that you don't have to bring a lot of raw materials. Imagine you need to repair a part of the aircraft or just for daily medical use. You can only bring the raw material, which are just cells, and then you can kind of transmit manufacturing information through genetic code in space. So drastically reduce basically creating genetic or cellular Lego blocks that could realize long-distance communication, coordination of manufacturing in space. So here above, it's my part of the presentation. I hope you guys enjoyed it. And then we are going to have a panel discussion about challenges and opportunities in all the advanced materials that I mentioned, applied in automotive industry with a group of experts later on at 11 o'clock. Thank you.
This may be too detailed a question to ask, but I'm going to go for it anyway. The virus battery really caught my interest. Is it known what chemical reactions are going on inside the virus to act as a battery?
So based on my research, as I understand it, it was using battery DNA, the structure of the DNA chromosomes as a template for the electrics kind of transmission, basically templating using the DNA chromosome structure, if that makes sense.
So is there a good resource for 3D bioprinting, like a diagram or a chart? Anything that you might recommend?
Yeah, there's a book kind of incorporating the latest advancement in 3D bioprinting. It's called Biofabrication from MIT Press. I think it's a recent book from 2021. So,
Hi. So I enjoy 3D printing with just earth materials on the ground. And with that, we use robotic G code. How is that different than the genetic code that you were talking about that would be used in space?
well, actually, it's very similar, but the big difference is the medium. So we normally print with filaments, plastic filaments, whereas the printing process of cellular raw materials would be very different. So also, I'm thinking, I imagine the encoding and decoding of information would be quite different. So we normally store 3D models in a material form. In the format of STL file. Whereas you need to translate the STL files into genetic code. Then so STL file, I imagine, is a binary code, whereas in genetic code it's like 4 letters. So the encoding and decoding. So there will be an encoding and decoding process.
Great.
Yeah.
Okay, we got a question up there.
As bioprinting really kind of takes off, I was curious what thoughts you might have around how the raw materials start to become sourced as bioprinting becomes more of an industrial service.
Currently, I think this sourcing raw material has been addressed in most like cellular agriculture industry. So they are all like cellular based as raw material. So basically cultured in the lab from the ground up, if that makes sense. So you don't have to like really think about sourcing it from living organisms or I think there's a standard process to create a cellular medium culture for various purposes.
Outside of any of your current use cases or anything that you've mentioned already, do you see any other roadblocks in implementing the materials?
Bioprinting materials, you mean?
Yeah.
Roadblocks. I think it's definitely scaling up because normally in many material development process, scaling up is always a challenge, especially in this type of bioprinting materials, whereas the process is it's happening in a highly controlled environment, which requires many resources to be put into to create all these new facilities and pairing infrastructures basically for testing at industry level. It's very challenging. So this also can be seen in most of our spin out or startup partners, whereas doing biomaterial development requires many just seeking the process of seeking basically industrial scale infrastructure, and also new materials coming out, and there's lack of appropriate regulations. So you don't know which standard you need to adhere to, but you kind of required some standard to be met to actually to get into the market. So there is a huge lack of relevant regulation and roadmap basically for this type of novel biomaterial development.
Thanks. I'd like to go back a little to the virus batteries. So we got kind of the molecular, foundation of it, but how does that get translated into some usable form?
So it's a very early stage research based on my understanding. Currently, how does it translated? I think they haven't really scaled it up into vehicle battery scale, but they're still doing testing within the lab. So yeah, I'm not sure I can answer that question so far.
Has there been any significant progress in the fusion between self-healing biomaterials and soft robotics?
Yeah, definitely. I think later on, Professor Julian Vincent can tell you more. But right now, I know self-healing materials are not just applied in that I mentioned, fiber reinforced materials, but it also applies in definitely polymer can realize self-healing. It's a dynamic polymer network, which can be applied in many kind of soft materials. And also, there's research about creating artificial muscle tissues that can actually self-heal themselves. So they are biomaterial in itself, not necessarily biomimetic material. So from both way, I think there are quite a few applications in soft robotics. Thanks, everyone.
Good.